Welcome to Mongoose channel. When building a connected embedded device, one of the first decisions is the networking stack. Two common choices are lwIP and Mongoose. lwIP is a widely used embedded TCP/IP stack. Mongoose is an integrated networking library that provides TCP/IP, web server, MQTT, TLS, and firmware update support in a single package. In this video, we start a practical lwIP versus Mongoose benchmark to measure integration complexity, flash and RAM footprint, and overall production readiness. This is part 1 of the comparison. Here we build the baseline firmware and integrate the TCP/IP stack. Later parts will add a web server, device dashboard, MQTT cloud connectivity, firmware OTA updates, and TLS. For the benchmark, we use an ST Nucleo F756ZG board, so the results are real, reproducible, and close to what you would see in an actual product. Before comparing lwIP and Mongoose, it helps to look at how networking functionality in embedded firmware is typically structured. The following diagram shows the common stack of layers used in a connected device. Each layer has a specific role. The driver talks to the Ethernet peripheral and sends or receives network frames. The TCP/IP stack implements IP, TCP, and UDP. TLS adds encryption and authentication. Protocols implement things like HTTP or MQTT. The application implements the actual device logic. With that model in mind, we can now see how lwIP and Mongoose fit into this architecture. On the lwIP side, the stack is built from several separate components: the STM32 Ethernet driver, the lwIP TCP/IP stack, embed TLS for security, an example HTTP and MQTT code. On the Mongoose side, the same functionality is provided by a single integrated library. Mongoose includes the network driver, TCP/IP stack, TLS, and application protocols. It also provides extendable examples and tools like Mongoose Wizard for building device dashboards. One important detail: Mongoose can also run on top of lwIP. In that configuration, lwIP provides the TCP/IP layer, while Mongoose provides TLS, protocols, and the application framework. In this benchmark, we compare lwIP against Mongoose, used as a full networking stack. First, we create a minimal bare metal STM32 project using CubeMX and VS Code as the build environment. This project is our clean baseline for all later measurements, so it contains only the hardware setup needed for the benchmark and nothing more. We configure the MCU to run at 216 MHz. Enable the random number generator. Bring up UART for debug output. Set up the LED GPIOs. Enable the Ethernet pins. At this stage, there is still no networking stack, no web server, no MQTT, and no TLS. Just a tiny firmware skeleton that boots and runs on the Nucleo F756. Once the baseline firmware is up, we make it print the amount of free RAM over UART and record the flash footprint of the build. These numbers give us the reference point for everything that follows. After that, we will integrate lwIP and Mongoose separately on top of exactly the same baseline and measure how much code size, RAM usage, and complexity each solution adds. GCC with newlib implements standard C functions through weak syscalls, so printf ultimately calls _write. By overriding _write to transmit data over UART, all file output functions, including printf, are redirected to the debug console. We override _sbrcar, which malloc uses to grow the heap, so we can track heap usage. CubeMX already generates an sbrk in sysmem.c, so we disable it and replace it with our version. The linker script defines 320 kilobytes of RAM. The _end symbol marks the end of the data section, which is where the dynamic heap begins. The heap grows upward as sbrk moves the break pointer, while the stack grows downward from the top of RAM. Free RAM is simply the space between the current heap and the current stack pointer. Now we update the main superloop to print free RAM once per second. By default, a CubeMX CMake project only produces an ELF file. Add a post-build step to generate the raw.bin flash image file. Build and flash the firmware. Record free RAM and flash usage. With the baseline firmware in place, the next step is to integrate lwIP. We start by making a copy of the baseline project. This is important because the same clean baseline will later be used for the Mongoose integration too, so both stacks are measured on exactly the same foundation. Inside CubeMX, we enable lwIP and keep the default configuration. Add DHCP initialization so the board can obtain IP address automatically from the local network. Then we add lwIP processing to the superloop, which is the bare metal equivalent of telling the stack, wake up, do your job, handle packets, don't just sit there looking expensive. Once the interface comes up, the firmware prints the obtained IP address over UART. After that, we verify that the board responds to ping. If ping works, we know the MAC, driver, ARP, IP stack, packet RxTX path, link state, and basic timing are all working together. If ping does not work, nothing else will. With lwIP integrated and ping confirmed, we record the new flash footprint and free RAM numbers. Now let's try to change lwIP configuration settings. Open CubeMX and navigate to the lwIP configuration panel. Most options there are low-level TCP/IP stack parameters. For engineers who are not familiar with TCP/IP internals, these settings are difficult to understand and even harder to tune correctly. We classify lwIP configuration tuning as hard. Now let's integrate Mongoose into the same baseline firmware. As before, we start by making a copy of the baseline project. Mongoose can be added through CubeMX middleware, but in practice it is simpler to copy the library directly from GitHub, because the core library consists of only 2 source files. Go to the Mongoose GitHub repo and copy the following files into the project: mongoose.c to core src and mongoose.h to core inc. Create a configuration file, mongoose.config.h. This file controls all build options and allows the firmware to enable or disable specific features. Add mongoose.c to the build system. With the files in place, we add Mongoose initialization to main.c, create a Mongoose instance, and add event processing to the superloop. Build and flash the firmware. Record the flash footprint and free RAM numbers, and verify that the board responds to ping. Now let's try tuning the configuration. All Mongoose build options are documented. The number of options is relatively small, and the settings are easy to understand even for developers who are not networking experts. So we classify Mongoose configuration tuning as easy. After integrating both stacks on top of the same baseline firmware, we can compare the integration effort and resulting firmware footprint. The goal here is not to measure networking performance yet. We simply measure how difficult it is to bring each stack to the minimal working state, and how much code and memory it adds to the firmware. Both stacks are straightforward to integrate, But lwIP is harder to configure due to its large number of low-level TCP IP tuning parameters. In the next sections, we will build on this foundation and add real networking functionality such as a web server, device dashboard, MQTT connectivity, TLS, and firmware updates. Those steps will show how the two approaches behave in a realistic embedded application.